Hi, and welcome to a discussion of geophysical properties of the Earth's interior. We're going to talk about three things: heat, gravity, and magnetism in this section. We'll start out with sort of thinking about how heat changes within the Earth's interior and why, and then also what is the cause of some of the material behaviors at some of the layers within the Earth. With gravity, it's interesting. It's useful for evaluating what's inside the Earth. We get a signal, of course, by measuring gravity, but it doesn't really correspond specifically to one kind of rock or to the geology, and so oftentimes we need models and other kinds of data to tell us something about what's really in the Earth's interior. And then finally, magnetism, which is a geophysical property that will tie back into seafloor spreading and plate tectonics in general. Right, so if we take a look at the Earth's interior with regard to heat, we don't have a thermometer, but we do have something we call the geotherm, which is a modeled temperature from the Earth's surface, right, all the way down to, this is going to get us down to the center of the Earth here. And we're getting down close to 5,000 degrees Celsius. And it's actually almost as hot as the outside of the sun. The outer layer of the sun, I believe, is called the photosphere. And so it's pretty warm, and you'll notice that it's pretty smooth in our interpretation here of what it looks like because it's theoretical. We know that Earth's heat is caused or comes from two places at least. One is the leftover residual heat from the bombardment during the formation of the planet, the formation of the solar system. But we also know that it had to have uranium, thorium, or it has to have uranium, thorium, potassium in sufficient quantities to keep Earth's interior as hot as it is for as long as it is. There are a number of planets that appear to be tectonically inactive out in the solar system, and they probably don't have enough heat to keep things going. They also may lack other things like water in sufficient quantities as well. What we see, though, is the Earth's heat increases rapidly from the surface down to about 100 kilometers. After that, it kind of increases a lot more slowly. So in the first 100 kilometers, we're getting almost 1,000 degrees of change. And then in the next 3,000 kilometers, right, we're only getting another 1,000 degrees or maybe 1,500 degrees of change. So the Earth's geothermal gradient is very steep at roughly, let's say, 25 degrees Celsius per kilometer for the first 100 kilometers. And then after that, it drops down to maybe half a degree C per kilometer. So this is a steep gradient here. This is a reduced gradient. And we know that because the Earth's interior is solid. And if we know what the Earth's interior is made out of, and we know how waves pass through it and behave in it, then we know what the melting temperature of that material is at given pressures. And we know that it's solid, so the temperature has to be less than the melting temperature of that material. But what was interesting is to look at the melting curve, right? So this we've seen before, way back in chapter, was like 6 or 7. You can see this is the temperature across which rocks began to melt. And so if anything to the right of this red line here should be starting to melt or should be liquid, everything to the left should be solid. And what you see is the Earth's temperature gradient crosses that here at a small position, right? The geotherm crosses the melting curve, and that is a position where we have partial melting in the asthenosphere. That's why we think the asthenosphere is, or that's what we think makes the asthenosphere partially ductile, or I should say partially molten and ductile, is that it is very close to the melting temperature of that material right there, just above it even. Okay? We come down to the core mantle boundary, and we see here again the temperature in the geotherm exceeds the melting temperature for iron, and this explains why the outer core is liquid. And then as we go back here, the temperature, we interpret the geotherm to be at a temperature that is on the left side or to the left or in the solid zone of this position relative to the melting curve, which gives us the solid inner core. Okay? Gravity is something that is constant if you take a physics class, but we know as geoscientists that if you go measure gravity across the Earth, you'll find it isn't constant. In fact, you'll see that wherever the crust is thicker, there's more gravity, and that has to do with the relationship between between force, mass, and distance here. Where we add mass to the system, we end up with a larger gravity, right? So if we add a thicker crust, we get more mass up here, and we get a bigger force. If we minimize the distance, okay, that's going to also change the system. So making it a smaller distance, we're going to actually increase the force, and a larger distance between the objects, we're going to reduce the force. In the Earth, it's not between two objects in the same way that you're seeing here, like mass A and mass B, which would be mass A and mass B, but it's really between, someone. If you take one of these here, and we'll just put a dot here, we're assuming all of the mass of the Earth sits here, okay? And we're measuring gravity up here with our gravimeter. We're measuring it in gals. 1 gal is 1 centimeter per second per second. So, we're measuring gravity of 9.8 meters or centimeters per second, or 900 centimeters per second, 900 gals, right? So that's the base level measurement, 980 gals, I should say. If we have a person up here, right? Gravity is pulling on this person, the mass of the person relative to the mass of the planet. So the mass of the person becomes A, the planet is B, okay? And the distance is the diameter of the planet. So we can calculate the force of gravity acting on that person. If we put a mountain here, we add mass, we also add some distance, and those two could potentially cancel themselves out, but it turns out we're going to get more gravity or less gravity, depending on how close you are to the Earth, and also depending on how much mass is below you. So if you put a high mountain made of a high density material, you're probably going to get an increase in gravity, but you also might find that there are places where we get a decrease in gravity, right? So let's just take a look at an example. These are gravitometers down here. All this thing is a can with a weight in it. It seems like it should be a really sophisticated device, and it has a spring. It's all been calibrated. So this thing up here with the spring and the weight being pulled down by gravity like this, that's actually what's in this box, and you carry it around with you. You make measurements, you locate yourself, and you measure gravity all over the surface of the Earth and create a contour map, just like you did for making one for topographic maps. But the idea is that, if we have normal gravity would be like this in the middle. This is all limestone, and goes into the mantle and into the core down to the center of the Earth. Step to the right, okay, we add a cave, right, which is a big hole. Air is much less dense than rock, and so there's less there's less pull on the weight at the end here, and so it sort of goes back up, and so we get less gravity. And down here we've got more gravity because we've got a big dense piece of metal, iron, nickel, copper, all that's denser than rock, significantly denser, and so we're going to get more gravity in that case. Here's an idealized profile. You can see the gravimeter. That's what this little ball with the spring represents, right? So where is gravity the highest and where is it the lowest in this system? Well, this is the anomaly we measure, right? Positive versus negative gravity anomaly. So just a change in gravity, really, relative to some place that you normalize it to. And what we see is there's a general increase in the amount of gravity here, positive value for the gravity. It gets very low here and then increases back here again. So this is a positive anomaly, more gravity. This is less gravity. This is more gravity. And this is a geologic cross-section. Well, what's causing this increased gravity here? Turns out basement or crystalline rocks that have a density of 2.7 grams per centimeter cubed. As you move to the right, though, you get into rocks that are less dense at 2.4 grams per cubic centimeter. These would be sedimentary rocks, right? So you might be coming off, off of the shelf and into the oceanic crust here, right? That would be one interpretation. So like on the east coast of the U.S., as you move offshore, you get into sedimentary rocks, you get into thinner crust. Now, here you hit salt, which has a density of 2.1 grams per cubic centimeter, and we see a very low gravity anomaly, so a minus anomaly measured in this case mellogals, okay, and then positive again as we get back into slightly more denser sediments. And so that's basically what you end up doing, is calculating or making measurements to calculate or determine this, what we call the Bouguer gravity anomaly. And then you have to come up with an interpretation of the geology, right? So these are the rocks. This is just a measurement of force. And so this can be quite tough to do and requires multiple interpretations. This is not an easy process. You will have many cross sections. You'll have to add in different densities and try to model or back model the actual gravity you get by putting in different types of structures in here. So that's usually how geophysicists do this. They make the measurement and see what it looks like. They look at the geology, and then they start adding in different kinds of rocks and different kinds of sediments that they can see at the surface, and then project them down to the Earth's interior to try and get explanations, which are essentially hypotheses, to explain the various Bouguer anomalies that they see. Okay, this is just an example, again, of different kinds of magnetic anomalies that you can see in the Earth's interior. Again, you have positive magnetic anomaly, or possibly a negative anomaly. Usually you don't have negative magnetism. But the idea here is that if you have magnetic minerals in the rock for some reason, you might get in a positive anomaly. So sedimentary rock, and then you have an ore body like something that contains iron in it. In these limestones here. Here we have gabbro, which contains more magnetic minerals. We have diorite, which also contains some more magnetic minerals. And so we get a positive magnetic anomaly. Okay? Now, magnetism plays into the Earth's interior in other ways as well. The Earth's magnetic field is not generated by these rocks. The Earth's magnetic field is generated electromagnetic field or magnetosphere is generated in the Earth's interior. These would be shallow magnetic anomalies that we might use a magnetometer to measure the amount of essentially relative magnetism to try and interpret what is in the subsurface. Again, you don't know what's there until you drill down. In this case, you might be able to test it. But in the core is where we have the Earth's magnetic field being generated. And this creates a kind of field that extends out from the Earth. So if this green ball here is the entire Earth, it comes out from the bottom and back up into the top and helps to deflect the solar winds and things emanating off of the sun. Okay? But periodically, what we found is that this polarity, positive to negative, reverses every tens of thousands of years. That's really to millions of years in scale. And it does it without warning. It does it abruptly, apparently, and it does it with no real clear systematic fashion. It is one of the things we do not really have a good handle on why this happens, or what it looks like exactly when it does happen, because we've never really lived through one of these experiences. But we can use this field to interpret the magnetic behavior, the magnetism of rocks, and to apply it to tectonics. Ultimately, what causes this is convection in the core, creates an electrical current. The electrical current creates a magnetic field, and so that magnetic field is then sort of surrounding the Earth. All right, so that kind of wraps up our discussion of Earth's interior, and we will move on to apply some of these topics, especially magnetism and the measurements of magnetism in rocks and magnetic minerals in rocks, to understanding plate tectonics.